Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is EET 122, Digital 2. Today we're going to have a discussion of asynchronous counters. Asynchronous counters should come very easy to you because we've already discussed what a basic counter application and JK flip-flops. And again, this is predicated on the belief that you are very well versed in a JK flip-flop. So if you don't have an understanding of JK flip-flop, please stop, rewind, hit the JK flip-flop until you feel confident in that, and then we're going to discuss counters. Okay, so an asynchronous counter. Asynchronous, again, remember, means without regard to a clock or something's offbeat. Basically, a counter, it's going to progress from 0 to whatever you want to count to, but all those bits are not going to be changing at the same time. There's a bit of a ripple delay. Okay, so let's go ahead and draw a basic counter here. Okay, this is our setup for a basic counter. What we're going to do is we're going to feed this one a clock signal. And again, it's a negative edge detection device. And the output from the first stage is going to be fed to the second stage's clock. Okay, what do we have to do to J and K? For both stages, those need to become toggle mode. Basically, both tied to +5. Okay, that is one version of an asynchronous counter. Okay, and here we have our clock signal. And again, since we're using negative edge detection, let's go ahead and highlight our negative edges right there, right there, right there, and right there. And now we have to determine where our LSB and MSB are. So this right here, that's Q0, that's our LSB. This right here, Q1, that's our MSB. What are we making here? A 2-bit binary counter. Okay, so let's assume Q0 and Q1 are in a reset condition, i.e. they're 0. And again, they're in a toggle mode. So at this first negative edge right here, I'm going to just highlight the negative edges as to where they are. So this is our Q0, our LSB, and our Q1, our MSB. Now in a perfect world, Q0 would change right here. It would toggle right there. It would toggle again right here. And it would toggle again right there. And so on and so forth. And you know what? I messed something up here. Let's remove that one. Okay, because now we're looking for the negative edges on this. Because the second stage is, again, that is also a negative edge detection device. So where's the negative edges here? It's there and there. So the only times that Q1 would change are those 2 time increments right there. So in a perfect world, we would expect Q1 to change like this. And what we get here, 0, 0, whoops, 0, 1, 1, 0, 1, 1, and then we've recycled to 0, 0, and the sequence repeats itself. Okay? So what we've got is a 0, 0, 0, 1, 1, 0, 1, 1. It's a binary up counter which recycles to 0 and starts again. But since we know that we are not living in the ideal world, there exists something called propagation delay. So let's turn our attention to strictly the first gate and what happens with the propagation delay of the first flip-flop. Well, it's going to change the output of Q0 ever so slightly. So given these are our negative edges again, we're still concerned with those negative edges of the clock cycle. But be aware that there exists a certain propagation delay for that clock signal having negative edge for the output Q to toggle from 0 to low. There exists a finite time, let's say 3 nanoseconds. So our output Q0 in actuality, even though the negative edge occurs there, there's a 3 nanosecond delay. And I'm just assuming that that is 3 nanoseconds. And then again, negative edge occurs here. There's a 3 nanosecond delay before it toggles. So we haven't really changed the operation of Q0, but we have changed when it occurs. There's a 3 nanosecond delay. It's still going from the 0101, i.e. half the frequency of the clock. So it's operating correctly, but with a slight delay. Okay. Now, what happens though with Q1? Well, the negative edges for the clock cycles are occurring here, and here, and here. But the negative edges for Q0 are actually occurring here, slightly delayed, and here, slightly delayed. So Q1 is going to go along and toggle on these negative edges. But remember, there exists a certain propagation delay for this gate of, let's say, since they're identical, 3 nanoseconds. So there's another delay of 3 nanoseconds between here and here when Q1 toggles. And again, I know that's when the clock is getting its negative edge, but this is when Q0 is getting its negative edge, but Q1 has a slight delay after that, so it's going to go here. Okay, so see what I mean about asynchronous? It's not happening at the same time. The counters are not changing simultaneously. And if you think about it, if you happen to land, ideally our progression should go from 0, 0, 0, 1, 1, 0, 1, 1. If you happen to land right here, what is your count at this moment? Well, you've gone from 0, 0, you stepped up to 0, 1. Suddenly you're back for a brief moment of time to 0, 0. Now you're 1, 0. Now you're 1, 1. And then at this brief moment of time right here, you happen to be at 1, 0 before you recycle back to 0, 0. So asynchronous counters have these natural glitch states which can occur because the LSB and MSB, or by extension any of the digits in between, are not occurring simultaneously. Okay, so there's a brief windows, and you could easily get around that by using a strobe or something like that. Okay, take the sample then, take the sample then, take the sample then when it's stable, take the sample then when it's stable. So setting up your timing correctly, but you do need to be aware that natural glitch states exist for asynchronous counters. And these are what's called ripple counters. And it makes sense because using the same terminology we used in adders, a ripple, it takes a bit of time to get through here, which affects this guy downstream. Everything affecting everything else downstream. Okay, so there are a bunch of different types of counters, and this is just one version of them. This is an asynchronous up counter 2-bit using negative edge detection. Okay, we can make a 3-bit counter by adding another flip-flop to the stage here. But let's do something a little bit different. It's still going to be an up counter, but it's a different type of up counter. So here is 3 positive edge detection devices in close proximity. And we're going to feed a clock to this one here. It's a positive edge detection device. Okay, what are we going to do with all the J's and all the K's? Well, they're all going to be in toggle mode. They're all in +5. And that's what that looks like. but that's way too many wires. So I'm actually just going to go ahead and remove that. Just understand that all J's and all K's are tied to +5 and they're all in toggle mode. So the trick here is for this type of clock, we want an up counter still, but we've got a positive edge detection device. Take your not cues and feed those to the next stage. And you'll see exactly when we do the timing diagrams how this works. So let's draw our timing diagrams. So there's our clock signal right here, and again we're using a positive edge detection device. So let's highlight where our positive edges are occurring. Let me use the same color marker. Positive edge. Okay, so we're concerned about our stages. I'm going to go ahead and draw this as this is stage 0, that's stage 1, and that's stage 2. And again, we want to read our LSB here and our MSB here. What do we want to take? Do we want to take Q or not Q? Since we want to make an up counter, we're going to take our Qs. And again, so that's going to be Q0 because it's coming from stage 0, Q1 from stage 1, Q2, which is our MSB because it's coming from stage 2. But we have to take into account now the not Qs for stage 0 and 1. So yeah, I know we're going to be doing positive edge detection from stage 1 and 2, but what are we positive edge detecting, the Q or the not Q? Well, it's the not Q. So we should probably draw what the not Q is. Okay, so let's go ahead and draw let's do stage 0's Q0 and not Q0 simultaneously. Again, positive edge detection device every time because J's and K's are all hooked up to 1, so we're always in toggle mode. Anytime we hit a positive edge, we're going to toggle. But what I just drew there, is that really correct? The answer is no, because, well, first off, I messed this one up right here. Ideally, again, the perfect world, we should be toggling exactly at the positive edge. But remember, there is a delay in this stage. So anytime this clock experiences a positive edge, there's a slight delay before this thing toggles. That slight delay right there. Let's say it's, again, very tiny but still measurable. So let's go ahead and show what that looks like. So again, our toggling should ideally occur at these incidents right here. But we're going to see Q ever so slightly behind that. So what is not Q? Well, it has the same delay as Q. So for all intents and purposes, it's just the inversion of Q. So now, not Q is being fed into the clock of stage 1. So Q1 and not Q1 is what we need to diagram next. So where are the positive edges of not Q0? Right here, right here, right here, and right here. So ideally, our transitions should occur here, 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 and here. But we know there's a slight delay through that stage. So we're shifting over that same time increment. So let's go ahead and see what that looks like. And there you go. So according to our original clock pulses, which are right here, we've shifted over 2 time increments, one for the first stage, stage 0, and one for stage 1. Okay, so now we're 2 nanoseconds delayed. Okay, so not Q1. For all intents and purposes, it's the version of Q1 and it's suffering the same delay. And there's not Q1. Where are its positive edges? Right here and right here. So what does the output of Q2 look like? Well, it's going to be toggling anytime not Q1 has a positive edge, but it also is going to have a delay of, let's for this example, is 1 nanosecond. So what does Q2 look like? Well, it's just going to go along Q2 until it hits a positive edge right here, but there's a delay. So normally it would toggle right here, but it doesn't. It toggles right there. And normally it would toggle right here at this particular instant, but no, there's a delay right there. Still that same tiny increment. And if we go down, that one's not going to work. How about this one right here? If we go down this one, what have we delayed? Well, 1 nanosecond for the first stage, 2 nanoseconds for the second stage, and Q2 being the final and third stage, 3 nanoseconds. So it's a cumulative delay. We're just compounding these. And what's going to happen is, keep on adding these things up here. What we're going to do is look at this. We'll keep on adding these. What happens when our delay goes into the next positive edge of the clock? That's where you've got some problems. So there's a maximum clocking speed which can occur for an asynchronous counter. So you guys have used the 7493 in lab already. That's a 4-bit asynchronous counter. We're actually going to go into how that works inside. There is a maximum clocking speed for that listed on its data sheet. It says do not exceed such and such a speed. Well, the reason why is because you keep on making this clock faster and faster. I mean, look at this. Here's a clock that's going terribly fast. Look at all the positive edges that are occurring there. Well, you've already busted this up here, because anything beyond a 1-bit counter for that, you're already, anything beyond a 2-bit counter for that, your delay is just too much, okay? So the total delay time in this case is 3 stages. So let's pretend, again, we had a 1 nanosecond delay per cycle, and it's got to go through 3 flip-flops, through 3 stages. So the maximum delay we could ever have is 3 nanoseconds there before we start running into trouble. So what is the maximum clock frequency? It'd be 1 divided by 3 nanoseconds. 333 megahertz. Not a very realistic example. That's very good. If your maximum clocking speed, if you can run this thing at 333 megahertz, you're pretty happy, because as a matter of fact, I'm going to look up at the data sheet now. What is the 7493 maximum clocking speed? And its top speed, 32 megahertz. So yeah, not too shabby with 333 megahertz. So question comes to your mind, what did we count up to in our particular example here for this 3-stage counter? Well, remember, we're taking Q0, Q1, and Q2. So 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0. So we're getting an up counter. What's it going to count up to? Well, there's 3 stages 2 to the 3 is 8. It's going to have 8 total positions. So 000 all the way to 111. And that's it right there. It's counting from 0 to 7 and recycling back to 0. And when I say recycling, it's going back to its original state of 0, 0, 0 after it achieved 1, 1, 1. So key thing to remember, it's not occurring simultaneously. Q0 changes. Let's see, let's get a good example here. So Q2, notice how it's taken, it occurs right there. It goes to 1 right there. But Q1 has changed previously, and this one has changed before. So not occurring simultaneously. When is the valid time that you can read it? Right here, because now Q2 is stabilized at 1. Q1 is stabilized at 0. And Q0 is also stabilized at 0. Okay, the thing that comes to your mind about counters is, if this is to hold true, where this right here is the number of stages, do we always want to count 4 back to 0, 8 back to 0, 16 back to 0, 32 back to 0, 64 back to 0, and so on and so forth? Well, chances are no. I mean, we're a decimal society. We've got 10 fingers for a reason. So we want sometimes to count from 0 to 9 and back to 0, i.e. 10 decimal. So how do we do that using this system? Well, we're definitely going to have more than 8 positions, but we want less than 16 positions. So what are we going to do? We're going to have 3.7 flip-flops? No, we're not. We have to have 4 flip-flops to do this. But there's a trick, and the trick involves the clear. Because remember, every single one of these flip-flops here, dangling off the bottom of them, is an active low clear. So, stands to conjecture, if we got to the number we wanted to, i.e. we maxed out at the number that we want to get to, if we sent all 3 of these flip-flops a low, because remember that's active low clear, we could in effect clear them and force them to recycle early. And that's exactly what you're doing by a decade counter. A decade counter is going to count from 0 to 9, and it's going to force a clear on all the flip-flops. Then it's going to recycle everything to 0, and it's going to start back over until it gets to 9. And then once it tries to go into that 10th condition, it forces a clear and goes back to 0, and does the same thing over and over and over. It counts from 0 to 9, goes back to 0 to 9, back to 0 to 9. Okay, over and over and over again. So the trick in doing this is using that clear. And I'm going to do it on this particular example right here using our 3-bit counter. So let's say we want to have a mod 6 counter. So mod is a different term for some of the folks here, unless you've taken cryptography or numerical methods. You've seen it in math before. Mod is the modulus of something, i.e. what's the maximum number of positions. If you think about a 2 to the 3rd, a 3-stage counter, its mod is 8. It's a mod 8 counter. It can count up to 8 positions. I know it goes from 0 to 7, but that's 8 positions because it's 0, 1, 2, 3, 4, 5, 6, 7 back to 0. You got to count 0. That's one of the positions. So that's a mod 8 counter. How do we force this thing into a mod 6 counter? So we want 6 positions. So we want it to count from 0, 1, 2, 3, 4, 5. And when it tries to go into the 6th position, we want to go ahead and clear everything. So let's erase a bunch of these things and start over and create a mod 6 counter. Then we'll do a decade counter. Okay, so here's our 3-stage flip-flop, stage 0, 1, and 2. Where are we going to read our LSB? Right here, Q0. Here's our in-between bit, and here's our MSB, Q2. What are J and K all hooked up to? Well, they're all in toggle mode. So they're all hooked to +5, but I want to avoid putting all those wires in there. So just remember J and K for all stages are all hooked up to +5. Got a clock being fed in. Okay, ordinarily, if we left this thing alone, this would be a mod 8 counter. It would go from 0 to 7 and back to 0 again. So we want to somehow force a clear when it tries to transition from 5 to 6. So one of the ways you can do that is using a NAND gate. A NAND gate just hangs out here. And again, what's the truth table for a NAND gate? There it is. The only time it's low is when all inputs to are high. This sounds like a perfect gate for us to get an active low clear signal. So we want to definitely take our output for our NAND gate and tie it to our active low clears. Okay, key thing is, what do you hook up to this NAND gate to determine your mod? Well, we want to make a mod 6 counter, and ideally a mod 6 counter is going to look like this. It's going to start at 0, then to 1, 2, 3, 4, 5, but then it's going to recycle back to 0. So we want it to prevent it going into stage 6, which is 1, 1, 0. So the key thing here, let's feed that to the NAND gate, because that way it breaks the cycle when 1, 1, 0 is fed here into the NAND gate. It will clear everything, and you're going to start right back here. The problem is this 0. You could put an inverter right there, and do the inversion of that, but I'll show you a trick here. We'll just keep that as is right now. Again, what is this? What do these represent? That's Q2, Q1, and Q0. So this is the stage that we want to prevent it from going into. So Q2 is one of them, Q1 is one of them, and we have to invert Q0. So let's go ahead and make those connections here. And there we go. We've got anytime Q2 tries to be a 1 right here, Q1 tries to be a 1 right here, and Q0 is a 0, but we've inverted it right here. It's going to send an active low clear signal to every single one of those flip-flops and start them back here. Now there's a shortcut to this that's going to increase your reliability and cut down on your connections. Because a NAND gate only really requires 2 1s for it to work, you can actually delete that connection to Q0. You can leave it if you want to, but this is what's called partial encoding, where I know that you're trying to force it into state 6 here, and you want to avoid that. Yes, and to make absolutely certain, you could invert that 0 on Q0, but it would just increase your reliability because you've decreased the amount of parts that can possibly break by just doing Q1 and Q2. And that's entirely sufficient enough to provide an active low to clear all the flip-flops. Because why would you clear something that's already clear? Okay? So the timing diagram on this thing, you're going to see a brief momentary transition into this sixth state. I know you're going to be going along, and I'm going to start it at this stage here because I don't want to confuse anybody with. So that's 1, 0, 0. And again, that's MSB, 2 LSB, Q2, Q1, Q0. The next transition state, the next state is 5, 1, 0, 1. And now what you're going to do is you're going to see a brief momentary transition right there. Just a little quick spike. But then that little quick spike is going to clear everything, and you're instantly going to go back to 0 right there. Okay, you've counted up from 0 to 5 because we're a mod 6 counter. It's 6 positions. There's a brief spike on Q1, and there's a brief spike down below for the clear, a momentary, a brief 0 to get everybody back to 0, and you're starting back at 0, and you're counting back up to 5 again. 0 to 5, i.e. a mod 6 counter. So how do we make a decade counter, since that's the most important one? Okay, let's do the negative edge flip-flop version of a counter, and we're going to go ahead and feed it a clock, obviously. And here's our Q0, that's the output from our first stage, Q1, Q2, Q3, and again, this is the LSB, that's the MSB. Okay, so we've all got our active low clears. We definitely know that something has to do with this, and we want to make a decade counter. So, decade, 0 to 9. We're only going to count up to 9, but it's 10 positions. So, when it tries to go into binary 10, i.e. 1010, because remember what binary representation of 9 is that. As soon as it gets into this, we want to make an active low clear. So, this being Q3, Q2, Q1, Q0. It sounds like we would have to, let's do the hard way first. Do a 4-input NAND where we are inverting that one and that one. Q3, Q2, Q1, Q0. Again, that's the hard way. Let's do the easy way. There's only 2 values in here that are 1, namely Q3 and Q1. So all we have to do is take our NAND and Q3, Q1, and tie it to every single one of our clears. Anytime Q3 and Q1 simultaneously get a 1, it's going to force a big massive clear on, well, on all of them, okay? Knowing Q2 and Q0 are already clear. If they're already 0 and it's being cleared again, it's still going to be 0. So one could easily modify this circuit to do a mod 12. So let's go ahead and get rid of our connections here we want to make a mod 12 counter now. So mod 12, it counts from 0 to 11. And when it tries to go into state 12, we want it to clear. So what would it be? It would be just Q3 and Q2 to clear that. There's an example in your book where I believe it also makes a mod 12 mod 12 counter, but for some inexplicable reason they've only done this and this thing hooked up to +5. Yeah, that's totally a mod 12 counter, but is it applicable for everything else? No, it's not. It's only a mod 12 counter. You can't change this thing to anything else. For flexibility's sake, just tie all your clears together. Because if these guys are already cleared and you're clearing them again, it doesn't matter. Just make sure it's cleared, okay? So modulus, recycle, anything, the propagation delay, should be pretty comfortable with that, with this discussion of asynchronous counters. The last thing I want to discuss about asynchronous counters is the 7493 4-bit asynchronous binary counter, which you've already probably had exposure to. Okay, so the 7493 has 4 flip-flops, and again, I'm just going to remind everybody, all the J's and K's, they're all hooked up to +5s. They're all in toggle mode, but I just don't want to draw the confusing lines there. Okay, so notice, these 3 guys here are all hooked up to clock B. This guy right here, that's hooked up as clock A. So there's 3 functions of 7493. First off, it can just be used as a divide by 2 frequency divider. If you use just one of the flip-flops, it could be used as an mod 8 counter using these 3 flip-flops, and using these guys in combination, you can make a 16-bit, a mod 16 counter, a 4-bit counter. Another thing right here, notice the NAND gate that's dangling off the side, and that's connected to all the clears of all the flip-flops. So this means, depending on what you feed into R01 and R2, you can make different modulus counters. So let's go ahead and set it up as a decade counter. So the key thing to setting this thing up as a decade counter is knowing where your outputs are. So this one's obviously our Q3, our MSB, Q2, Q1. Well, where is the output for Q0? Well, what you're doing is doing a little bit of a trick here. Since these are negative edge flip-flops, just take the clock as clock in is the output for Q0, because Q1 should be half the frequency of Q0, and that is how you do basically a counter using one less flip-flop for your mod. Okay, so we are now going to set this up as a decade counter. So when do we want it to clear? We want it to clear when Q3, Q2, Q1, Q0, try to enter a state 1010. So take Q3 and Q1 and tie those to our NAND gate. And that again is being fed to every single one of those guys. This one doesn't really matter because you're not really using that one. So this kind of concludes the discussion about the 7493 and a whole bunch of discussion about the asynchronous counters. And like I said previously, if you're pretty well versed at a JK flip-flop and the basic functions of counter, this should have come as real easy to you.